maintenant d'appuyer sur le menu, il y a un qui va s'enlever et l'autre qui va se mettre.
C'est la même télécommande pour les deux. C'est fantastique. Welcome everyone to this second lecture on BGP. Tomorrow we'll start the lab session on BGP. The lab is already posted. You can already try if you're interested. And today, if time permits, we will also start with the application layer. Last week, we concluded with an example of aggregation. Which I'm trying to recover. Okay, I'll do it differently. 37. Voila, this is where we stop. Last week we saw that aggregation is desirable, particularly with IPv4, but is primarily easier with IPv6 in order to reduce the number of prefixes that the core internet routers have to manipulate and to look up in real time for every packet. Right? If you're a router in the middle of the internet and you have one IP packet, you look up for the destination IP address where in your table is the entry, and if your table is 500,000 entries, then you have to look up 500,000 entries for every packet received. So that's really is a bottleneck in the performance of the internet. That's why we try to perform aggregation. What we've seen last time is one of the side effects of aggregation is that the path that we receive might have some uncertainty about the AS path that is used, and this is expressed in the AS path by the OR construct, which uses curly brackets, so that we still bring the information. Here 1, 2 means the path goes through AS1 or AS2. Another side effect now is that we can be in this situation where AS4 receives receives two announcements, two BGP announcements, one that comes from a router in AS3 that is aggregated. That's what we saw in the previous slide. But perhaps AS2 and AS4 are also peers, in which case AS4 receives from AS2 this non-aggregated advertisement. Right? Because AS2 has no reason to aggregate. And the question is, now, if I am a BGP router in AS4, is it possible that the decision process at this BGP router designate both routes as their best preferred routes? Okay, can we close the poll? By the way, can I? No, it's not visible. I close the poll in 5 seconds. That's a nasty poll. First, it's a yes or no, so the chance of having strong negative grade is high. I try to avoid that in the graded polls. And second is one of those nasty things where if you think you know the stuff that not everybody knows, then you're tempted to give the wrong solution. The thing that is important in BGP and that not everybody knows, but that you should know, is that a BGP router can select at most one best route. And once and only this best route can be further propagated to other routers. So that's a temptation to say answer number 2. However, the answer is 1, because those are 2 different routes. So that's the main goal of this quiz, is to be aware that 2 overlapping routes are distinct routes. So the rule that you should choose only one does not mean that you should have only one way of going to a particular destination. It means along all the prefixes that you have for a given prefix, if you don't aggregate, you might have overlapping prefixes. For a given prefix, a route is different from another route that has a different prefix. What can AS4 do? We don't know. It depends on how the policies are programmed inside AS4, like you will do in the lab. If AS4 is happy with both routes, then AS4 will receive the 2 and will apply its decision process independently to each of the 2 routes. In particular, it may happen that both are kept if nothing in the policies prevents that from happening. Okay, assume it does so. We continue the game. So AS4 has accepted both routes, which I will show here. Okay, AS4 shows both routes. Now there is a packet from AS4 here that has to go, whoops, where's my pen? We have a packet, we are here, and we have a packet to this destination, 2001 Baba Bepth, which is in AS2, right? Probably. Which path will this packet take? I close in 5 seconds. And now the correct solution is the majority vote. In AS4, both routes are accepted. Therefore, we have in the routing tables both routes. Of course, we will see there are more details in the routing table than just the AS path list. But for this exercise, the information is sufficient. Now, when a packet goes to this destination, inside AS4, the routers will look up the forwarding tables and will do longest prefix match, which means they will choose the most specific route. The more specific one, in that case, is the shortest, the one that goes directly to AS2. So the packet will go directly to AS2. So this is how overlapping routes, in practice, the effects that the overlapping routes have in a case like this one. Yes?
Why wouldn't the packet stop at AS3 before going to AS2?
Because inside AS4 you have 2 routes. One for the prefix with 48 bit, another one for the prefix with 47 bit, and they go to different directions. The first route will go this way, the second will go that way. Okay. When you do longest prefix match, if things are well organized inside the network, you should go this way. Other questions? Now, what's the interest of having, yes? If the prefix match is the same, that means we have two routes. That's not possible. Okay? We can have, so if the prefixes are exactly the same, BGP will choose only one. We don't know. It depends on the decision process inside AS4. If all default values are used, and if AS4 decides to aggregate, that means decide to forget the announcement received by AS2, then of course the only announcement will be through AS3. The only one that is kept, and they will go through AS3. But in general, that's not done. If you're AS4, like here, and you receive those two blocks, one which is one route with a 48-bit block, another route with a 47, you might aggregate them, but you might aggregate them only when you pass them along to other ASs. Inside your domain, you may want to keep, in principle, you will want to keep this detailed information, except if you decide that the route received from AS2, you don't like it, because you don't like to have direct connection to AS2. But if you keep that route, for example, if there is a lot of traffic between AS4 and AS2, perhaps two labs doing super computers in physics that have a lot of data to exchange, then perhaps you prefer to go directly on this link. If that's the case, you will keep it. Now, what's the interest of having both an overlapping block that can do the same job as the non-overlapping? Well, it's in case of failure. If the link between AS2 and AS4 fails, as shown by this green cross here, then what will happen with BGP? In AS4, the BGP routers will sense that the connection to AS2 is lost, either physically or simply the keep alive mechanism between BGP routers will stop working. Therefore, AS4 will detect that all the routes that were received from AS2 are now to be withdrawn. So the BGP routers will withdraw them from their database, from their RIB-in, and will recompute the best path. Now, there is no path to that prefix, therefore it will be simply removed, which, if there would not be the other one, would mean that this prefix is not reachable. But since the other one is still reachable, it will stay. It's not touched by BGP. But when packet forwarding decisions come, of course, there will be only a match with the 47-bit prefix, and the packet will go to AS3. Voilà, we had the first glimpse of the interaction between BGP and packet forwarding. That's the topic of the next section, which is perhaps the most touchy in BGP. BGP is fairly easy to understand at the level we've done it so far. It does path vector routing, and in the exercises like the previous one we did, a domain is just like one thing, one AS, and then we view it as an abstract node. The difficulty is when you zoom inside a domain and there are multiple routers and how things play together, in particular the interaction with the interior routing protocol. The first topic in that category of practical and potentially annoying topics is how do we bootstrap the routes into the BGP process worldwide? So who decides to put routes somewhere? Because everything we've seen so far is how we repeat routes. A BGP gets from someone information about a route, gets it from several routers, and then decides which one is best, and if policy authorizes, forwards it further. Now, at some point, we need to inject the routes into this process. So this injection is called bootstrapping. Sorry. Sorry, this we said already last week, and we saw that this is done by either locally. Where's my bootstrapping slide? It was slide 34, right, which we saw at the... So this we saw already. That is our first... let's rediscuss that a bit. We saw that there are several ways to do it. The annoying thing about BGP is exactly that one. The good thing is every BGP decision process is well defined, but all the rest, there's lots of options. We will try to see what is the standard case. The standard case for bootstrapping the routes is called redistribute connected. That means a BGP router knows all the prefixes that correspond to all of its interfaces. Those are the connected prefixes. Redistribute is a terminology that is used by Cisco and by Quagga that we use in the lab. That means we pass information into a routing protocol that comes from somewhere else. So here we pass into BGP information that comes from the configuration of the interfaces. Redistributed connected. This is the, I would say, the standard case that I ask you to remember for a while. Now let's return to the rest of section 3. So now we have a way to pass to the world all the prefixes that are connected to BGP routers. The next question that comes, how does that go back into the forwarding tables? So that's the topic of this section here. What is the natural way of doing that? If we think of BGP as a two-layer routing, BGP being the upper layer, the lower layer being RIP or SPF or whatever you use in your domain, and then in addition you interconnect everything with BGP. Then the natural thing to do would be to do what is called redistribution. Redistribution into RIP of all the routes learned by BGP. So BGP, your BGP router in your local networks has learned about prefixes from the big outside world. Now the natural thing is to inform RIP of all those prefixes that exist, and then RIP will propagate them all over the network like its job is doing. So in other words, redistribution is like if a BGP router pretends that it is directly connected to a prefix that is an outside prefix. That's the I claim this is the natural thing because the goal of RIP or an internal protocol is to pass along the information about which network prefixes are reachable and how to go there. If we do this, the IGP, RIP, for example, the interior routing protocol, will pass the information to all domains. So if I have one border router in one part of my network that knows about routes that go to China, for example, it injects it into RIP, and then all routers in my domain will know that they have to go to this specific router in order to go to China. So that's the natural thing. However, it has a big problem. Which make it, if we do that in the lab, it will work. So we will play with it in the lab. But if you do it in a domain that runs RIP and is at the core of the internet, the RIP table will be 500,000 entries. So they will blow up, or your machine will hang, or something bad will happen. So the problem is that the interior routing protocol, most of them, not all, protocols like OSPF, that we will discuss a bit later, are able to manipulate huge tables. But protocols like RIP are not. Yes? Even with aggregation. The number of prefixes in IPv4 after aggregation is 500,000. Okay. So perhaps when IPv6 has become the only dominant protocol in the internet, and probably dead by then the number of prefixes will be 20 or 30,000 instead of 500,000, and then we can come back to it. But in the meantime, we have to do something else. Again, I insist, this is something that is possible, that is natural to do, and can be done if you have an interior routing protocol that supports it, that has been designed for huge stuff. RIP has not been designed for huge stuff. RIP is a low-key, low footprint protocol, doesn't use a lot of memory, doesn't use a lot of CPU, and its goal is to discover all the prefixes that exist in your local area network. In your local network, not local area, but local company network, you have in the very worst case 1,000 prefixes, not 500,000. So in practice, people do something else. which is automatically done by the software we have in the lab. It's called injection. Injection means whenever BGP learns about a route, ping, it writes it into the forwarding table automatically. In fact, in BGP, the set of routes selected by BGP are found in the routing table. So BGP uses the forwarding table of the node as part of its own database to write it down in practical implementation. So right now it's important to learn the difference between those words that in practice might mean exactly the same thing, but in the context of routing protocol, please make the difference between redistribution, which means pass from something into all the databases that a routing protocol has some information, that's called redistribution, from injection. Injection means you directly write into a forwarding table. The main difference is that the routes that are injected, they don't propagate. It helps only this router. If a BGP router at the border of your network knows how to route to China, it will route in its forwarding table. On this link, I can go to China. But the other routers will not know by this mechanism. So we will need something else so that all other routers are able to know this. Here is an example showing how it works. So on this screen we've lost the bullets, so I'll start here. Router R5, which is on the top, advertises the prefix 18.1. R6 transmits it to R2 via BGP. We call it iBGP, but remember it's the same BGP protocol with just rules about what can be repeated or not. Here R1 is a router that doesn't run BGP. It has a different color. It runs the internal routing protocol of this domain, but since it is in the middle, there is a priori no reason to run BGP. R2 is not on link with R6, but is connected indirectly to R6, and there is a TCP connection illustrated in orange or yellow, depending on your chromatic processing, that makes R2 and R6 BGP peers. Remember, inside the network, there is a BGP mesh that all BGP routers talk together over TCP connections that are possibly multi-hop. So R2 will pass the information to R4. Okay. Now, if we redistribute BGP into RIP, R6 will inject 18.1.16 into the interior routing protocol, as if the 18.1 was directly connected to R6. Now, here OSPF, if we redistribute, probably it's not into RIP, but in OSPF. So OSPF will do its job. OSPF knows R6 is directly connected, not directly, but is connected to 18.1. OSPF has a lot of space for information, so OSPF will put a flag saying this is an external route. And R1 and R2 will learn about that route. So when a packet comes to this destination, when a packet comes from R4 to this destination, when it reaches R2, R2 knows that in order to reach the destination to R6, it knows the shortest path, because through OSPF routing, it knows that it has to go to R1, R1 knows that it has to go to R6, and R6 knows it has to go to its interface 2222. Okay. So that's the perfect world. As I mentioned already, in practice we won't do it because it's too complex. This already mentioned. If we don't do it, we will have a problem that I will discuss in a detail. I'll skip that for a second. In practice, therefore, we don't do this natural thing called redistribution, and we do injection. But if we do just injection, we need another ingredient, which we haven't seen so far, And if we look exactly what routers do in practice, whoops. Injection that works only in combination with what is called recursive table lookup. What is that? Let me explain on this example. Here, if I am, or let me just explain perhaps on this example again. If I am R6, I learn a route to 18.1, but what is the information that BGP learns? There is one very important attribute. There are weights, perhaps, priorities, things like this, but one vital attribute is the next hop. So the next hop at R6 is an IP address like 2222. Right. What BGP routers do when they inject into the routing table the routes, they inject as next hop their next hop. So R6 will inject next hop 2222 in its forwarding table, which is perfectly okay. The next hop in a forwarding table has to be something directly attached on link. Okay. Now, if we do injection and not redistribution, R2, which is shown here in yellow, right? R2 will do the same thing. R2 learns from R6 this route. If R2 does injection, which is invariably always done by Cisco routers, R2 will inject into the forwarding table the entry 18.116 and next hop 2222. Right. Now if we do this, we break the IP architecture because the next hop is not on link. 222 is an internal prefix. Remember that the boundary prefixes have to be considered as internal by the two sides of the boundary, but it's not on link. Right. So if we do this, in principle, it should not work. Now, this is software, so things that don't work can be made to work by tweaking the thing twice. So we did one mistake, we need to correct by doing another mistake, or one violation, we need to correct it by second violation. This second violation is called recursive table lookup. So in addition to what we saw in a router, if you write in a forwarding table a next hop that is not on link, and if your router allows recursive table lookup, what it will do, it will, when it finds this next hop and it is not on link, it will try again. It will go again into the routing table and ask, how do I go to 2222? This is recursive in the sense we go to the routing table, we get an answer, and we use this answer to go again to the routing table. Like any recursive thing, you have to hope it will stop at some point, otherwise you're caught in a loop. So here's an example, another one. At R1, so let's assume the routing table at this router contains to this destination 10.1.16, next hop 2.2.63, and 2.2.63 is here, so it is not on link. Normally in a routing table, there is the next hop, but also MAC layer information, which is the physical interface on which you have to send it, perhaps even the MAC address to save you the problem of doing ARP if ARP was done already. Here, of course, there's no interface because it's not on link. Then what will happen when a packet to that destination, 10.1, comes at this router? First, we go to the routing table. We find 2.2.63. Then we go again to the routing table. Now, because the next hop is always a prefix that is inside the domain, normally, if your interior routing protocol works well, all the destinations that are inside the domain are reachable, so we know there must be an entry in the routing table that matches. Perhaps not an exact match like here, but there must be at least one entry that matches, which is the case here. And here the second match will be 222.33. So this is how recursive table lookup works. If we take it strictly speaking the way I said, that may mean that when a packet comes to a router, you will have to go twice to the forwarding table, which is bad, because going through the forwarding table in a router that's in the core of the internet is already the bottleneck, and the performance of the router. Doing it twice is making things worse. In practice, however, we can pre-process those things for any routing table which is typically coming from BGP that has a next hop that is not on link. Then it's very easy for the router to detect that this is not on link. And then instead of waiting for a packet to come, the router can write here some additional information on this line, so that, or put a pointer, a direct pointer to another line here, so making it a linked list structure, so that you don't look up the table twice. In practice, this is what is done. As you can imagine, the lookup tables in high-performance routers are highly optimized. So there are lots of tricks coming from courses like algorithms or principles of computer systems that are applied to speed up the access here. Okay, so the standard case for the implementation of BGP is to use injection at every BGP router. Therefore, also to use recursive table lookup. Let's see what happens, and that perhaps there might still be problems. In this scenario, R5 advertises 18.1.16 to R6. R6 advertises it to R2. R1 is not a BGP router, therefore it passes on the packets from R6 to R2, but it doesn't read them, doesn't process them. R2 injects the next 18.1.16 with next hop 222. That's the default behaviors of all BGP routers we have seen. Then let's assume a packet comes. A packet to 18.1. something. Here it's 111. Okay. Let's take this packet. When it arrives at R2, what will R2 do? R2 will say, oh, recursive table lookup, I need to send it to 2222. How do I go to 2222? That's easy, because 2222 is an internal address for me, so I know how to go, and the shortest path go to R1. The packet is sent to R1. What happens at R1? Here are a bit less nasty quiz. 3 possibilities. What is your best guess? Five more seconds. So the majority thinks that it is forwarded to R6 because R1 runs an IGP. I'd love to understand how. So imagine you are R1. You receive a packet to 18.1.1.1, which is an exterior prefix. So for the IGP, this prefix does not exist. Never seen it. Right? It would exist if R6 would redistribute it into IGP, but here we say we don't redistribute, we just inject. So this prefix is invisible to the interior routing protocol. 222 is visible, but R1, who doesn't run BGP, doesn't know that to get to that destination, you need first to go to 222. That information is known only to the BGP router. So 2 is certainly not the correct answer. It cannot be forwarded to R6 either because for the same reason R1 doesn't know that it has to go to 222. This information is not written anywhere in the packet. So sadly, the correct answer is it doesn't work. If you set up your BGP network like this, it doesn't work. You'll have a loophole somewhere. There's not enough information in R1 for this thing to work. So we have a problem. The natural thing is to redistribute BGP into the interior routing protocol, but that does not always work. You need a very powerful interior routing protocol. If we have RIP, we cannot do this. Yes?
Couldn't we ask R1 to do a recursive table lookup to be able to get to 2222?
Yeah, I'm assuming R1 does a recursive table lookup, like all the routers in this network. But the problem is recursive table lookup helps only if you find that to go to that destination, you have to go to 222. This information is not written in the packet. R1 received this packet, 18111.
Unless R2 sends something else to R1 to tells it.
Unless R2 speaks to R1, okay, but that would not be through the IGP. It will be through the IGP if there would be redistribution, but we said a RIP will blow up, so you need to do something else. What can that something else be?
Flag that says do recursive. We need to go to 222.
Or you need to pass the information that this specific prefix is reachable via 222. Do you know a method for passing that information? Yes?
Maybe we could run BGP on all routers.
Exactly, BGP. BGP does that. BGP passes to a router the information in order to reach that destination. Here is the next hop. In fact, that's the main thing that BGP does. All the rest is optimizations around that. The main thing that BGP does is to carry the information in order to go to that destination, go through this next hop, plus the AS path so that you can choose. So, not surprisingly, in practice, in the standard BGP configuration, you do injection, you do recursive table lookup, but that comes for free. All Cisco routers know how to do that. And 3, you need to run BGP everywhere, which means that in R1, you will run BGP, which is weird because R1 is not talking to the outside, but this is the standard configuration you will find in all core networks, of course not in networks like EPFL. So if you take the Swisscom core or the switch core, they have routers that may or may not be at the boundary of the network, but all networks in the core run BGP. Of course, you don't run all BGP in all routers of your company. If you're Swisscom, you have routers that participate to the transit, to the core, and you have the Swisscom internal network that is used, for example, for carrying IPTV and things like this, or the intranet of the company. Those networks don't run BGP. Typically, they are like EPFL connected to switch. They have default routes to the BGP core. So you don't run BGP in all routers of a company that has BGP, but typically you run BGP in all the routers of the core that makes the interconnection of this company to the rest of the world. That is what is done in practice. There are other solutions that could be thinkable, but the last time I asked people I know who worked in operators, they said never heard of that. Nobody does it. We could pass the information inside the packet instead of passing the information through BGP. We could very well imagine that when this packet comes at R2, R2 knows the next hop, so R2 could write the next hop into the packet, right, with source routing information. It's called loose source routing in IP. You can add an option that says in order to go to this destination, first go to this intermediate thing, which is called the loose source routing header. That could be done, but source routing has very bad reputation. In practice, it's disabled by all routers because it has been used for attacks. In practice, it's a very powerful means for attacker to divert traffic. You say, all traffic that goes to UBS, please send it to me first, and then I will forward it to UBS. Right? Of course, if you're an attacker, then you can try to find weaknesses on the flows and analyze them. A variant of source routing is encapsulation. You could put the IP packet inside an IP packet with destination address 222. So router 2 could do this. Right. You could do a variant called MPLS that we'll see a bit later, which is a bit like encapsulation but with different flavors. Typically only MPLS, if any of those is done. Encapsulation, like source routing, are not done for security reasons. Also for processing reasons. If you're a backbone router, you don't want, when you receive a packet, that you have to encapsulate it in another one. So that means you will also need to decapsulate on the reverse path. So routers of that nature are trying to get rid of packets as quickly as possible. So in practice, if we do injection, which we do in the most common case, we run BGP everywhere. Voila, those are the main difficulties in BGP. In order to understand them well, you will have to play with them in the lab. So in the lab, we will ask you to do the standard case, but also the non-standard case, which will work in the lab with RIP because the network we have in the lab is small. And then you will be able to play with all the various options and see the ones that work and the ones that don't work well. We will conclude with a few other bells and whistles that I've mentioned. In BGP, you can use various priority fields. So we will zoom on a few of them, not all of them. There are a large number of them, and their use is overlapping. In some sense, you can reach the same goal with various of those things. A very commonly used attribute is called the local pref. Local pref is used only inside a domain and is assigned by a BGP router when it receives a route from the outside. For example, here, a route to a given destination received by router 6 could be programmed to be associated with local pref equal 100, whereas the same route received from router R2 would be programmed with preference equal 10. Here preference, as the name indicates, the higher the better. So the BGP decision process will always pick the one that has the higher preference. Here is an example of how this could be used. Here we have AS4, which is here, sets local pref to 100 for all routes from AS3. So all those here are tagged with local pref 100 and 50 for those one here from AS2. As you can see, this is considered a less good link for whatever reason. Perhaps it has less performance, or we anticipate that it will cost a lot because if there's more traffic here, we will need to upgrade it and will cost a lot, whereas the other link perhaps is local. Perhaps those two connections are in an inter-exchange point where connectivity is multi-gigabit per second practically for free, whereas here perhaps it's a medium or long-distance cable. Assume R1 receives the route 10.116 from AS2, AS1, so here, and R2 receives, then it will set the local pref to 50, and it will, R1 will propagate inside AS4 with local pref 50. R2 will receive a similar route with a different AS path, AS1, AS3, and will put local pref 100. What will R3 announce to AS5? So R3 is this one. It will talk to some router, not shown here in AS5. What will it announce concerning the route 10.1.16? Here there's no trick, there's no overlapping routes. 5 seconds, and I close and we do the break. The majority is right here. Of course, the route will be this one. So we see the use of local pref is a fairly brutal and but powerful mechanism that says that AS3 prefers this route and therefore forwards it. And since the rule of BGP is that AS4, prefers this route, since the rule is you can announce only what you prefer, if AS4 really prefers the routes that go via AS3, that's the only one it can announce. Voila, we do a break. We'll say a few more things about BGP after the break in 15 minutes.